All right, welcome back to algorithms. So now we're all done with divide and conquer, at least as a unit in the course. And before we move on to the next stuff, I really need to make sure that we have kind of a good foundation surrounding graphs. So what is a graph? So a graph, and a lot of times if you're new to computer science or you're new to graph theory, you'll hear graph and you'll think, oh, we're talking about like a plot of a line. It's kind of an unfortunate accident of history that we call this a graph, but then we also call these other things graphs. So we're going to talk about the other kind of graph. So this is not a graph in this class. This is a plot, okay? So a graph is a particular kind of data structure. Really, in some ways, it's a family of kinds of data structures that represent networked data. So data structure for networked data. So what do we mean by networked data? Well, one of my favorite examples of graphs, and at some point I'm going to teach a class that's just focused on this example. One of my favorite classes of examples is a social network. Right? So if you think about Facebook, Facebook has somewhere in its database, it has a representation of who is friends with who. So you might think of a graph as a particular kind of a way of capturing friendship, right? So if we have a bunch of different people, we could call them, by our favorite CS names, Alice, Bob, Charlie, and Dana, or something like that. We might represent who is friends with whom by drawing lines between these pairs of nodes. So we might draw something like this: A, B, C, D. And what do these lines mean? If this is a friend graph, well, it means A is friends with B. It means C is friends with D. And in fact, everybody is friends with everybody except somehow C and B haven't met each other, right? C and B aren't friends in this graph. So you could also think of a graph as being a good way of representing something like, dependencies or prerequisites, right? So that's a common kind of a graph. You could think of a graph as representing a literal network, right? As being a representation of something like the fiber optic network in the United States. You could think of a graph as representing a more physical infrastructure looking network, like a transportation network. And there's a variety of different things. But at its core, a graph is a data structure that has two things, right? It has two chunks. So I'll write G to denote a graph. So a graph G is a tuple of two things, a set V and a set E. So these are both sets. V is called the set of vertices, or the vertex set, and this is the set of nodes. Right? So V is the vertex set of nodes in the network. Okay, so each of these is a vertex in this set. So in this example, the vertex set is a set containing A, B, C, and D. Okay. And it's a set, so we're not going to impose a particular ordering on it, right? If there's any ordering on this set, that ordering is going to come from something other than the graph itself. Okay, so V is the set of nodes, and then E is the set of connections, right? Or the set of links, or the E actually stands for the set of edges. So this is called the edge set, right? And so you can think of these, in more common English phraseology, this is the set of links. So there's a link has to exist between a pair of vertices. So that means that the edge set contains a bunch of pairs of vertices. So in this particular example, we can write the edge set as AB, right? The pair AB represents a link existing between node A and node B. So AB, AC, AD, what else do we have? So that's all the A links, and then we also have BD. We also have CD. right? And that's the full edge set of this graph. Okay, so a graph is any data structure where we have a vertex set, so a set of things, or a set of people, or a set of nodes, or a set of locations, or something like that, and then an edge set defined as a set of pairs of those things, right? So anytime you have something that's defined as a set of pairs, you can represent that as a graph. Okay, and so there's a kind of an ongoing question, which we'll revisit many times in this course, about how do you represent a graph in a computer, right? So if you try to write it down like this is quite cumbersome, right? And so this is a representation of the graph that looks a little bit like just a list of the edges. And in fact, I could just write down this, just the list of edges, and that would give me, that would specify the graph, right? As long as I have some kind of thing that connects the different A's and say, hey, these A's, every time I write A, that refers to a particular vertex. This would be a legitimate way of representing this graph, but it turns out it would be it'd be challenging to write algorithms that use that natively. Okay, so in general, what we're going to want to do is represent graphs in a more algorithm-friendly way. And there's essentially two ways of doing this. And whenever I say there's essentially two ways of doing this, I'm basically saying, don't expect this to be like the end of the story, but in this course, this is how we're going to treat it. And this is frequently how you'll run into graph representations. So representation number 1 is an adjacency matrix. Okay, so if I have n nodes in my graph, then this is an n by n matrix. Okay, so the size of the matrix only depends on the number of nodes. Okay, so suppose V equals V1, V1, V2, dot, all the way up to Vn, then the adjacency matrix is an n by n matrix. Then we get an n by n matrix. And so let's just think about using an adjacency matrix to represent this graph. Right, so I've got this graph down here. How would I represent this graph using an adjacency matrix? Well, what I would do is, so this is a 4-node graph, so it has to be a 4 by 4 matrix. And the reason it's 4 by 4 is because I associate a node with each column and each row. Okay, so in this graph, or in this adjacency matrix, I'm going to have 4 columns and 4 rows. And I'll think about labeling the columns and rows with the names of the nodes, or the vertices. So A, B, C, D, A, B, C, D. By the way, I will frequently use the term node and vertex interchangeably. Unless I tell you otherwise, those two words mean the same thing. The same thing with link and edge. I'll use those two terms almost totally interchangeably. So the adjacency matrix looks like this, and the rule for an adjacency matrix is that if an edge exists between two nodes, then I put a 1 in the corresponding cell in the adjacency matrix. Okay, so for example, there is an edge between A and B, so I put a 1 in the A, B location. I also put a 1 in the BA location, right? Because here, if there's an edge between A and B, there's also an edge between B and A. Okay, so there's also an edge between A and C and an edge between A and D, so I'll put 1s in there as well. I have an edge between C and D, so I'll put a 1 here, and then I'll put and here. And I have an edge between B and D, so I'll put a 1 here and a 1 here. And then I fill the rest of the graph, or sorry, I fill the rest of the matrix with zeros. Okay. Right, so if I write the adjacency matrix as X, so let me just call this X. So then I would say Xij, the ith row and jth column, is 1 if edge and I'll just write it like this. I'll write it totally formally. So if ij is in the edge set, okay, and it's a 0 if edge ij is not in the edge set. Okay, so this is ith row, jth column. Okay, that's an adjacency matrix, right? This is the full story of an adjacency matrix. So notice that the way I've drawn this adjacency matrix, the diagonal, right, this thing is all zeros, right? So the diagonal is zeros. If the diagonal has ones on it, then what that represents is that there is an edge from a node to a node. In some contexts, that's a sensible thing to do. That's frequently not going to be the way we'll be writing adjacency matrices in this class. Generally, I mean, there will be some scenarios where it makes sense to think about, what a self-loop means in a graph. But that's why, so you'll notice that it's all zeros down the diagonal. That's because I've not drawn this graph with self-loops, right? I've not drawn this graph with edges that connect a node to itself. Although sometimes you will see that being a reasonable way to go. So additionally, I've drawn this graph as what's called an undirected graph, right? So an undirected graph just is a graph that doesn't have arrows on the edges, right? So if there were arrows on the edges, then this adjacency matrix would not necessarily be symmetric. But notice that as written, if I reflect this thing across the diagonal, it's symmetric, right? If there's a 1 here, then there is a corresponding 1 here, okay? And so the reason for that is that this is an undirected graph. So those are just a few things to kind of carry forward with you in time. So diagonal represents self-loops, and the matrix is symmetric in the linear algebra sense of symmetry, where you reflect across the diagonal. The adjacency matrix is symmetric if the graph is undirected, right? But I could just as well, for instance, I could just as well have this be a directed graph where, say, the edge only points from A to B, and then I would say, okay, there's a 1 still in the AB location, but then a 0 here. Okay, that would be one way of representing a directed graph, where the direction of the arrow matters. For starters, all we're going to think about is undirected graphs. There will be cases where we look at directed graphs later on, but for now, everything is going to be assumed to be directed and lacking self-loops. Okay, so this is an adjacency matrix, right? It's an extremely useful object for certain kinds of computation about graphs. And the thing to notice about it is that the space it takes up is proportional to the size of the vertex set squared. And the space it takes up is not a function of the size of the edge set. So space for adjacency matrix is big theta of the size of the vertex set squared. So if I write this is an aside. If I write this with the vertical bars on the outside of the V of the set, this means the size of the vertex set, or I should say number of vertices. Vertices. Okay, so it's proportional to the size of the vertex set squared, and that's just because I require a spot for either a 1 or a 0 for every possible pair of vertices, and I've got to fill in all the spots, and so I've got a matrix that's that has V down one side and V across the other side, and so the total number of spots I have to fill is V squared. Right, or the size of the vertex set squared, or the cardinality of the vertex set squared. Okay. So in the next video, we'll talk about a different way of representing a graph that has a different space requirement, and can be used for different things. And part of the story of the course is every time we come to a graph algorithm, we'll have to specify how the choice of of representation of the graph affects the runtime of the algorithm. And we'll do that a little bit today as well.